Hello and welcome to this workshop. In this workshop, we're going to have a look at FOMCON Toolbox in what we refer to as the model-based control design workflow. So this is a kind of tutorial for which you will also need some files. So please go to this website over here, which is referred to by a short URL. And when you click on this one, you will actually get the files. Now in this one you will find the tutorial PDF itself, and then you will also find supporting slides, which we will have a look at a bit later. And there's also data. This is the data that will be used throughout the tutorial. So what I will do with this data right now is I will actually take this one and extract it into a pre-configured folder. So now I have the data, and of course in order to follow this tutorial you also need FOMCON Toolbox, which you need to download. So let's close this down, and here the second link, if you go to this one, then you will discover FOMCON Toolbox GitHub repository. And from here you can just simply download the toolbox by clicking on the code button over here. So click on the code button, then choose download zip and save. Once you save the file, and it went actually into toolbox folder that I prepared, just extract the contents into this folder. And then you can remove the source archive. Now, one thing that I should note here is that be careful with MATLAB path and with drive path specifically. So just to be on the safe side, I decided to create a _MATLAB folder in the root folder of my Windows C disk, system disk. And then I just created 2 additional folders, data and toolbox. Bear in mind that if in the path that you're downloading and installing the toolbox to, if in that path you have some non-Latin characters, that could lead to problems. So to be on the safe side, you can follow my lead with this one. So now we have both data, which we will need, and we have the toolbox here, but it is not installed yet in MATLAB. So let's proceed with that task. So I use MATLAB R2021A. And of course you can use an older release of MATLAB. If you have that, I guess up until R2012B, it should work just as well as in my case. However, if you are experiencing some issues due to your MATLAB version, please get in touch with me and we will figure it out together. So, first thing that we need to do is to install FOMCON Toolbox in MATLAB. So what that equates to actually is just inserting the toolbox path along with all the subfolders into MATLAB path. So the easiest way to do this would be to enter the toolbox directory and then right-click on the folder that contains the toolbox, and then choose Add to Path, Selected Folders and Subfolders. Once you do this, all of these functions that comprise FOMCON Toolbox will become available. And so you can then use all of these functions from anywhere in the command window or using graphical user interfaces. But it will only last until you restart MATLAB. So if you want to actually set this path for good, so you picked a good place to install FOMCON into, and then you want to proceed with saving the path, what you need to do is you need to click on Set Path over here and choose Save. Now, if you are in the lab environment where you may not have admin rights, this may not work. And for the purposes of this demonstration, I will not save this path. However, you can do it if you do have the necessary rights for writing the path file or the path definition file of MATLAB somewhere in on the disk. Okay, so we have successfully installed FOMCON, and in order to control that, I will go back one folder and to underscore MATLAB, and because I'm not in the folder of FOMCON, what I will do now is I will type in FOMCON, FOMCON, and if everything is installed correctly, you should see a graphical user interface like this. This is called FOTF Viewer, and by the way, this tutorial assumes that some previous knowledge, that you have some previous knowledge of control systems and control systems toolbox in MATLAB, so that you can get up to speed quicker with what we are discussing here. If that is the case, then probably you realize that FOTF Viewer is a similar application to LTI View, which is a standard control systems toolbox facility for analyzing linear time invariant systems. So with FOMCON, we also have this FOTF Viewer. And let me just really quickly go through what it is, so how it can help you quickly study fractional order systems. So on the left over here, this pane over here, is where you will find the models, primarily, of course, fractional order transfer function models, right? On the right-hand side here, you will find the tools that you can use to analyze those FOTF objects. So let's add an object. So let's call this one SYS1 for system 1. Zero polynomial we can insert as strings, so we can say something like S plus 1, as it is mentioned here. And for the pole polynomial, let's type in something like 0.5 S to the 1.5 plus 3. Okay? And click on OK. Now you can see that in this list, we now have system 1. And by the way, the error that you're seeing here is, I don't really know what it is. I just unzoomed using the Zoom It application, and MATLAB reacted to that, so I have to check it out. But in any case, now we have the system 1, and we can proceed with system analysis. So you can click, for example, on View in Console, just to see what kind of fractional system you have. Then you can do the stability test here. So click on that one, and looks like the system is stable. There are no roots in this red area here. So system seems to be stable. And then what you can do is you can also analyze time domain and frequency domain characteristics. So for example, for this system, let's do the step response from 0 to 30 seconds with a step of 0.1. So let me zoom in again. Let's see if MATLAB says something about that. No. Okay, so from 0 with a step of 0.1 to 30. And let's do the simulation now. And it looks something like this. Okay. And also let's plot the frequency domain characteristics of the system using Bode diagram. And here it is. So as you can see, once again, FOTF Viewer is just a convenience graphical user interface for studying fractional transfer functions. Let's now have a look at the slides, because I want to discuss a few things about FOMCON. So, and specifically, I want to discuss the structure of the toolbox. So we have seen currently some of the features that are on top here. So some of these features, which are responsible for implementation of analysis. Uh, so this module is basically for time domain, frequency domain analysis of fractional ordered systems. However, we also have three additional modules which we are going to have a look at today. So we have the identification module, which is used to identify fractional order models from experimental data, and it's possible to get time domain and frequency domain data in there to get the models. Then we also have the control design module, and in this one can be used for obtaining controllers, conventional ones, conventional integer order controllers, and also fractional controllers. And today we will have a look at the comparison of those two. Then we have the implementation module. This one can be used to actually implement, or rather to prepare the controllers for implementation, for real-life implementation. And we are going to briefly discuss this as well today. Here we have continuous approximations, we have discrete approximations, which are probably more interesting to the majority of engineers, since digital implementation is easier. Of course, what this means is that we also have analog filters, digital filters that implement fractional systems here. Okay, so let us proceed with the tutorial. So first of all, consider the problem statement here. And the problem statement basically refers to an academic example, so we are not going to look at a real-life system today. However, we are going to learn about how you would go about studying also real-life systems using FOMCON Toolbox for MATLAB. The hope is that by going through this tutorial, you will be able to go through the model-based control design workflow for any system that you have that can be modeled using fractional order transfer functions and which can be controlled with FOP80 controllers. So the academic example goes as follows. You have a certain black box system about which you have very little information. However, you do know that the control input signal range is between negative unity and unity, and that the output range of the system is between 0 and 2. As always, our task is to control the output of the system by compensating the closed loop with a relevant controller. So, what do we have here for data? What we have here is two sets of data called P underscore ID underscore V1 and same V2, which contains some experimentally collected data which we need to use to identify a model of the process that we need to control. And based on that model, we then design a controller for it. And the controller has to fulfill the specifications in the time domain and the frequency domain so that the control loop performs exactly as we want. So for reference, for example, settling time should be less than or equal to 40 seconds, overshoot and error band both 5%. And then we have frequency domain, gain margin, phase margin, and also phase response at critical frequency. Omega c must be as flat as possible to ensure robustness to gain variations. Okay, and we are going to work on these problems using FOMCON Toolbox. So we have the following tasks here, and we're going to go through them step by step. Okay, so the first task is to actually identify a model. So let's go ahead with this task. I will clean the command window, and you can call the TF identification tool in two ways. First of all, you can go back to FOMCON, and here you can go to Tools, Identification, and Time Domain. Or you can do a quick shortcut and type in FOTFID. And by the way, let me quickly also make the font a bit larger so that it's easier to follow what I'm doing. So FOTFID. Launch it, and you're presented with an interface like this. Now, right now, we don't have any data experimental data that we can use for identification. So let's get some data in there. Go into the data folder. And in the data folder, double click on experimental_data.mat, which contains the experimental data that we are going to work with. Now go back to the interface, and next to FI data objects, which is in the middle over here, click refresh. And you should see our data sets imported successfully into this one. Okay, now, of course, before doing any identification, we should look at the data. What kind of data do we have? So go to the menu over here and choose Data and Plot. Data and Plot. And this is our first data set. Let's also have a look at the second one. Do the same thing. And we have these two guys. So looking at the first data set, I can see that there is most likely some nonlinearity in there, because there's a corner at this point, right at 40 seconds, we have a corner. If you zoom into that, you can see that there's a corner. This is not characteristic of linear systems. So I would use this data for identification, but given that probably this is a dead zone, what I would do is I would cut out the linear portion, because we start from 0. So the initial condition should be 0, by the way, since we're using fractional order transfer functions and we assume 0 initial conditions. So I would use the first point over here, and I would cut all until this part with the corner, because, well, actually there are two corners here. And this gives me a range from 6.1 seconds to 40.1 seconds. And it will, of course, cut the excitation signal as well, or the system input. And then I would use the second data set for validation purposes. So let's do this. In order to cut this one, you can use the trim function that is available directly in this plot. So you can go to Data and choose Trim. And then I would call this one ID1_t. So let me just zoom in this one. So the new workspace variable name would be ID1_t. And then I would keep data from the 6.1 to 40.1. And then just click OK. And then you should see the new graph. Let me zoom out again. You should see the new graph with this newly constructed data set based on our previous data set. Okay, let's close these down for now. And what you can do now is you can involve that data set in the identification procedure. But right now I don't see it. Although even in the workspace, you see that there appeared FI data, data set ID1_t. Okay, in order to actually see that one, or use that one, what we need to do is going back to the identification tool, just again click refresh over here. And once you click refresh, because they're sorted in a kind of alphabetical order, you will see ID1_t appearing at the top of the list. And now we're going to actually use it to identify the model. So remove fix checkmark from this one. And it always makes sense to start with the simplest possible model. So let's make it 1/s+1. Additionally, we will enable static gain identification, which ensures that we do get a system that does have a static gain. And keeping free identification for now over here, and then we just do the identification procedure. Once I click identify, and by the way, you can see a button like this in my interfaces. Uh, this is related to Display Fusion software, so unless you have it, you will not see these buttons. They are quite convenient for certain purposes, but just so that you know, and they're not distracting you, know that these are related to a different software that I use. Anyway, so when I click identify, this additional interface appears, which shows us the progress of identification. You can even track this progress later on when you go to view performance graph. You can see the basically you can see how many iterations it took for uh, identification performance index to go from 5 all the way to kind of 0. It's never identically 0, of course, but still. So looks like it converged. Let's close this down. And here's our model over here. And don't forget that the static gain is actually in this box, so it will not be shown in here when you have this enabled. Okay, so we have this model, but there's oh, by the way, let's see how it did. So go to model, and here you can click validate to see the performance with the initial data set, and the fit is 99.45%, which is excellent. And let's try the validation data set as well. So choose that in FI data objects, and then let's see validation of this one. Fit is 95.24%, which is also excellent. I can see that there are some unmodeled dynamics in there, but with a fit like this and looking at the way that the two response curves nicely coincide, I don't think that this is a big problem right now. I think this is a very good result. In fact, let's check the first one with residual analysis, and we can see that there are almost no dynamics present in here, so we can consider this as white noise. So we also passed the whiteness test, at least with the first data set. But now there's a bit of a problem with this model, and specifically you can see that the order, well, maybe not so clearly, let me again zoom in. So the order of the model is 0.69743. This is not very good for fractional systems. We want to keep things tidy. So at the expense of a bit of accuracy, perhaps, we will trim this one. So you can just trim this out, but then we need to correct the model so that it could take that one into account. So in order to do that, take the static gain over here, copy it to the zero polynomial descriptor, and then choose here, instead of free identification, choose fixed exponents. And once you do this, so make sure that you have the first data set selected, and just click identify again. So there's some correction to the model. And now, since we don't have static gain explicit anymore, we also need to normalize the model. So you can go here, go to actions, and click on normalize. And what this will do is it will simply take this guy over here and divide all the coefficients by that one. So we end up with something like this. Now, let's see how the residuals go. Still good. If we go to the second data set and choose model validate, we have this one. No, I will not even do the residual test here because I can see that there are some dynamics present here, so it will not pass the whiteness test. So anyway, now appears that we have a decent model for control purposes, or for model-based control design, definitely. So let us now save this model. And the way that we do this is there's a button over here at the bottom of the interface called Export System. So click on that button. And the workspace variable name is GP1. You can name it otherwise, but I will use GP1 for the purposes of demonstration of other things. So GP1. Okay, stands for G, a transfer function, P is planned, and 1 because maybe we will have another one. Okay, so click OK. I zoom out, and we can now close this down. Actually, let's keep it open because later there's another another problem that we need to solve. So for now, let's go back to the first data set and just make it smaller. This one we can close down. Okay, so according to this one, we have solved the first task. We did not consider the lag parameter in this one. You can do this, but bear in mind that the rest will be a little more difficult since delay systems is a different kind of beast. In any case, in case of this system, I did not notice any significant delay, so perhaps this is justified. Okay, second point. So we need to design a classical PI or PD or PID controller for the plant, setting the design specifications as required in the control problem. And then we need to design an FOPI or FOPD or FOPID controller subject to the same specifications. Okay, and here are some instructions how you can do this, but let's go back to FOTF viewer. This time we will launch PID optimizer through going through another interface. So if you go to fractional PID design over here, you will see the design tool opening up. This is very simple. This is just serves the purpose of quickly trying various parameters for a control loop like this. And by the way, this is in fact what we are working with today. So now from here, tuning optimize is what you want. Okay, you can also specify the system right away. Like for example, let me close this down, refresh the list, and choose GP1 in FOTF viewer. So when you do this one, go to Tools, Fractional PID Design, and it will appear over here. And now what you can do is you can go to the menu and choose Tuning, Optimize. And you get the FOPID optimization tool. So with this one, we are going to proceed with optimizing the response of the system to the desired specifications. So let's go through the checklist of what we need to change. So first of all, tick this box over here, enable zero cancellation for non-proper LTI systems. This is important. I will not go into details what that does, but be assured that we rather do this than receive error messages from MATLAB due to some problems. From theoretical and practical perspective, there is no difference. Where tuning is concerned, we just add some additional negligible dynamics to the system, and we can therefore simulate it if it's non-proper. Okay, and now this pane over here is where you will set the parameters for either a conventional PID controller or a fractional PID controller. So right now, we are requested to tune a conventional PID controller. So what I will do is I will set some parameters up. Lambda and mu right now are 0.5 each. So what I will do is I will simply make them ones. And what I will do next is I will click on this drop down here and choose fix exponents, which makes it so that we are now only tuning the gains of the controller, and the orders are left alone for the optimization purposes. For constraints, I will choose something like 5s, the maximum constraints, and minimum will be 0. You can also quickly do this one here, changing these parameters through this convenience dialog at the bottom. Now, looking at the dynamics of the initial system that we have modeled, I think 100 seconds is enough for simulating it. Then we have these parameters that we leave alone for now. But we do want to tick and use Simulink for system simulation over here, because we also want to set up control law constraints so that we can monitor control law saturation. Okay, so we enabled this one, and here on the right hand side now, the first optimization algorithm, we will keep it optimized. Then the performance metric, let's choose EITAE, which stands for integral time absolute error. Gain and phase margin, so phase margin, gain margin was 15, phase margin was 60, but initially these are minimum um, values. And in some cases, it makes sense to do exact, try to achieve exact specifications, because otherwise your optimization problem may be poorly set up. So in this case, what I will do is I will set this one to 120 degrees, and I will make it exact. And a good starting point actually is 60. But for this system with some prior knowledge, of course, I will start from 120 just so that we can um, save some time on this one. We will leave noise and disturbance rejection alone for now. Critical frequency and gain variation robustness also for now. And then let's have a look here. Control law constraints. This makes sense to enable, so I will enable this one, but it will only be available if you also choose use Simulink for system simulation down here. And the minimum was -1 and the maximum was 1. Next, generate report. Highly recommend you tick this box, otherwise you will not see like the plots of the resulting control system. And then maximum number of iterations, since we're using optimize, which internally uses null-der-me, then it makes sense also to set it up here, maybe for 50 iterations or so. Now that we have everything set up, it makes sense to save the initial configuration. So I will go to File, and by the way, this is a very powerful technique, as we will see, to kind of keep track of these different configurations. And so here I will say Save Configuration, and there's test control over here, which I will overwrite and just save this one. Yes, I want to replace it. Good. So actually now we are ready to do the optimization. Let's click on Optimize. And the process UI appears here, and it will show us progress information about the optimization procedure. Now, because we did tick use Simulink for system simulation, it might take a little bit of time to initialize the simulation and so forth, but then you will see that there's progress. The performance index is initially very large, and this is due to the fact that we are introducing the constraints, in this case gain and phase margins, as penalties into the cost function. Some technical details about the optimization. Okay, but then when you see when it reaches reasonable magnitudes, the performance index I mean, in this case you know that, okay, we have fulfilled the specifications and now we are in feasible zone, let's say. So let us proceed with this one. And once the optimization completes, or it runs out of iterations like it happened here, then consider the response. Okay, so this is the time domain response of this specific control system, closed loop control system. And as you can see, the initial one had a large overshoot and went down, but this new one, although it does have saturation at the beginning, sometimes it's not really feasible to get away from saturation. So you see that the response is quite smooth, and so it's could be considered a good one. Now let's see this one, the Bode diagram. If we go into characteristics and then check out minimum stability margins, we will see that the initial system had a kind of phase margin, but this one, if we enable all stability margins, you will see that in fact the phase margin is, as computed at the crossover frequency, is very close to what we specified, which is 122 degrees. Also, we can see from this one that the closed loop is stable, which is of course what we want. And another thing is that we almost for free have achieved the robustness to gain variations specification. Now the phase response at this point is not completely flat, but it's flat enough for many purposes. And we will actually, when we tune the FOPAD controller, we will also enable that specification. Anyway, this is very good for a start. So let's use this one. And by the way, it seems to me that KD tends to 0, so I would actually remove it right now. I would set it to 0. And in order to see what that does to the system, what you can do is you can tick simulate only over here. And then you can click on simulate, and this will show you the result of this change. So you can see that we still have the response, the smooth one. Then we also have this one. Let's see, characteristics. It's now less flat, but again, we will tend to this later. So once you have done this, you can go to File, Save Configuration. And now I will name this bid controller 001. I will save it. Now, whenever you load it back, it will restore all of these parameters, so you have to type them in all over again. Okay, so let's now proceed to the next task. Actually, before we do that, perhaps we will tune also a fractional controller. Now for this one, I will actually restore this parameter over here. And I will remove fixed exponents and keep this at 1. And what else I will do, I will enable the critical frequency specification. But before I do this, let me see where exactly it was. And the crossover frequency. So if I do something like this, again, see the stability margins. So the frequency is 0.5 radians per second. So let me enable this one at 0.5. And be sure to untick this omega high thing. We will not need it. Every other parameter we will keep as they are. And now remove simulate only so that we can optimize again. And let's do this one. Keeping all these parameters the same, let's optimize. Initially, again, we get a huge magnitude of the performance index, which goes down after a while to something feasible. And while it's doing this, let me comment on these actions over here. So stop will take the current parameters of the controller, and it will return them to the graphical user interface. Whereas if you click abort, the parameters that you had before will remain here. Okay, so here are the results, and let me again see the stability margins. If I zoom into the specific part of the plot, we can see now that the phase response is more flat, which is what we want, since that was specified. But perhaps I would give this one a few more iterations actually, so let's optimize again and see if we can get some better results from it. So it seems that lambda parameter, which is the order of integration, goes from 1, actually below. And you can see that the performance index is still improving. So sometimes you can maybe allow more iterations just to see whether there's some hope of getting better dynamics. So let me also check out this one. In view, we have performance dynamics. So if you click on this, you can see how the performance index changed along with the parameters of the controller. So we have a bit of a more sluggish response here. But let's see. So in frequency domain, still very flat region. If we go to stability margins, flat region, which is a favorable property that we were after. Okay, so let's proceed from this one then. And I will once again go to save configuration, and I will call this one FOPID controller 001. And I will save it here. So both of them are now in the current folder. All right, now we are ready to actually test these controllers with the so-called real system. So for that, open object control.mdl over here. So this is the Simulink model. And this block represents the controller, but right now there are question marks on top of it. So why is it? This is because this block accepts actual configurations from the folders which are accessible to MATLAB. So if you double click it, you will see that it expects a structure mat file name, and the structure is fpid_optim. So let's first test our PID controller. So PID_controller _001, and the other parameters you can leave as they are. So once you type this in, you will see that it recognized it as a discrete optimal PI lambda controller because we didn't have the D component in there. So let's test it with this one. Just run this model. And you can see something like that, and then you can also do the auto scale operation. So you get a response like this one from the PID control. Let's keep that in mind, so let's use print-to-figure to store this information. And let's replace this controller now with the FOPID controller. That is easy because the way of how we name these files. So just insert FO in front of this one. Now we have the D component, but that's because we have optimized again there. And let's run it. And this is the result. Let's compare it to PID control. So I would say actually that the results here for FOPID tuning are worse in some ways because here we have a lot of noise in the control law, and maybe this is because of the D component, which amplifies noise. So let's go back and let's fix some of those issues. So in the FOPID optimization tool, what I would do right now, perhaps first of all, let's see what the characteristics are. So I'll simulate the system to see the characteristics. And we have frequency 0.428. And we have something like that. So let us do the following. Let us decrease a little bit the phase margin here. Let's make it 110. And then for this one, for the differential component, I want to reduce the negative effect it has. So let's make it 0.5 to start from. Okay. And maybe also we change this parameter a little bit. Maybe we give it a little less bandwidth, make it 0.35. Let's see how it goes with that one. Remove simulate, and then click on optimize. If you keep Simulink open with this one, then it will blink like this, which I will remove so that it is not it's distracting me too much. And let's see the performance, whether it will improve. Okay. So in fact, with this one, we now have an overshoot, which I don't think is very nice. So let's go back again. Let's make it 115, and 0.45 would be the critical frequency. And let's try to optimize this one again. Okay. So now we have a response like this. Let's check the stability margins. Okay, the phase is flat over here. And we have a bit of an overshoot over here, but still pretty much acceptable. So, and also notice that lambda parameter over here went to 0.56. So clearly we have some, there is reason for using a fractional PID controller in this scenario. So once this is done, let's save the configuration, and we will save this under FOPD controller 002. And now let's go back and check out what happened, what changed in this so-called real control. So choose this one and run this again. Okay, so this is the result. Let's again compare it with the PID one, unless I closed it. Might have closed it, but I will simulate it again. Just bear with me here. So that one was PID controller 001. So run that simulation. And then we do print a figure. Move this away for now, and then go back to our FOPID controller. And here are the results. Let me just put them side by side. So looking at this picture here, still with the FOPID controller, we have a little bit of noise in the control law, but the controller itself is more accurate. So assuming we have obtained optimal PID tuning and optimal FOPID tuning, this one would be superior to this one. However, you are free to experiment with these files and try to obtain let's say a fair comparison. If you can for this specific process tune a PID controller that offers superior performance to FOPID controller while simultaneously fulfilling all the specifications, please let me know. Anyway, this just goes to show that we have a generalized tool which can be used to tune these controllers, and we can compare the performance of PID versus FOPID, with FOPID having more flexibility still than a PID controller. In any case, I think this result is valid, so let's see what else we need to do. So we also need to identify a higher order model and try it try to design a controller with that one, but I will leave part of this at least as your let's say homework exercise. Okay. Yeah, so I will leave this 0.5 for you to do in the interest of time. Okay, so for this one, what we will do now is we will have another identification round. So I will show you some things with respect to identification. So let's hide this clutter for now and focus on the time domain identification tool. So what it says in the instructions, what it can do to get commensurate order systems using this tool, you can quickly, let's reset this to 1. And for this one, you can generate initial guess model for the pole polynomial as suggested, starting from 0.15. And we have order 5, which is suggested to change to order 3. And then we have pole polynomial and generate, and so you get a generated pole polynomial. So for this one, in order to ensure that this is a commensurate order system with a commensurate order of 0.15, what you do is you fix the coefficients, fix the exponents, just as we did with fractional PID design. And then what you do is you just click on identify. Remember to check the FI data object that you're using here. So identification proceeds forward, and then you can plot the results of validation for this one. In fact, let's use the second data set to plot the results immediately. So choose this one here and then choose validate, and oops, something is wrong here. So I guess this commensurate order does not work as well. Let's try the next suggested one, which was 0.25. And reset the pole polynomial to 1, and for this one just click generate to get this guy over here. And then not forgetting to change FI data object to ID 1_t, click on identify again. And once the identification process is concluded, again go to change the model here, go to model validate, and the same problem as with the previous one is present. So let's check out the final commensurate order, which was 0.35. So generate it here, and I reset the 0 polynomial, choose the first object here, and again go to identify at the bottom. Click identify, and after a while we get the model, go to this one, and model validate, and this one is a little better. Actually, this one is a little better. So perhaps if you continue choosing these commensurate orders, you will finally find one that works really well. Perhaps you can also play with the order, so to get a good fit with this model. So I suggest you try it, see what you can do, and when you get a coherent model, then you can proceed to retune the controller, and in this case I mean retune using the optimization tool. Okay, so we have this one, and I will not use this model myself, but we have 2 more items on our list. The first one, when we go back to FOPAD optimization tool, we can click on take values over here, and what this will do, it will transport it to fractional PID design tool that we have seen earlier. And in this one, now we have a button which says realize controller. Click on this button, and then you will get to the fractional PID implementation helper. And this one will allow to see, with given specifications and with given sample time, you will be able to see, like for example, here we choose discrete time approximation is matched pole 0 and 0 pole gain and so forth. And we can plot the approximation versus the original controller. And in the frequency domain, you can see whether you get a match and whether the match is in given band, and from this assess whether the controller can be implemented efficiently using digital means. So for this one, I think it's okay. And what you can do now, and by the way, you can use continuous time approximation, but we're interested in discrete time approximation. And when you use this one, you click save. And then in MATLAB, you will see that there is a D1 variable now, which is ZPK, a 0 pole gain format. And from this one, you can actually get the SOS arrays. D2 SOS D1 will give you exactly that. And now this one, you can implement using the provided tutorial code in C language for infinite impulse response filter implementation. So you can use those generated arrays and plug them in here, and then you will have essentially implemented that fractional order PID controller. Okay, and the final item on our list today, we're getting on top of the hour, but bear with me for just a bit longer. So now, what we need to do is we need to discover the benefits of retuning controllers. So for this one, open a file in this directory which says object_retuning_control.mdl. Open this file. It's another Simulink file with the following contents. So here we have what's called an original control loop over here. This is the PID control loop, assuming that we had an initial PID control loop. It was used to control this process over here. And you can see that there's a switch here, which says enable retuning control. If it's in this position, so we have it connected to ground. In this case, the retuning loop, which is this one, is completely bypassed, and you will get the original dynamics of the control system with the original PID controller. However, if you flip the switch, you will then have the additional control loop here, which will, through the reference signal, influence the internal loop so that it becomes a fractional, so that it would possess at that point fractional dynamics. So let's do this one. So there are some instructions needed to actually implement this. So we need the original parameters of the PID controller, which are here. And then we also need the parameters of the optimized fractional controller, which are here. And then you just open this block over here. And in this block, you need to first set the parameters of the FOPAD controller that you want to introduce into the existing control loop via this reference manipulation. So what you do is you just simply copy these parameters. And after that, you go to the PID controller block, and then from here you copy the parameters to the other fields over here. Okay. So once that is done, let us now compare the performance of these two control loops initially with the original PID controller, and then we will enable the retuning controller. So let's run this one. Okay, so the response with the original controller is not great, as you can plainly see from this picture here. So we have huge overshoots. In the end, it's more or less the signal converges to the set point, but this is an acceptable performance according to our specifications, of course. So let us enable now the fractional retuning loop by flipping the switch. And here we go. All of the specifications are fulfilled. The controller is also more accurate. And you can also see that with the retuning method, we don't get as much noise in the control law anymore. So it's an additional benefit from using this approach. So what this means is that if we have an industrial system with an original PID control loop that is performing suboptimally, what we can do is we can model that plant that we are trying to control, in this case, this process over here, by collecting data from it, maybe in closed loop or open loop experiments. And then based on that data, we actually identify a fractional model as we did today. After that, based on that model or based on those dynamics, we design a controller, a fractional PID controller, for example, like we did today. And based on this fractional PID controller, now we can introduce the dynamics of the fractional control loop into the original control loop via retuning control. And this is exactly what you see here. So that concludes the tutorial. Thank you very much for your attention. Hopefully you were able to follow the tutorial with the video. If you have any additional questions or concerns, you can write to me via this email over here. You should also be aware of an open source implementation of FOPD controllers, which is available here, and the corresponding paper will also be presented during TSP 2021 virtual sessions. So you can look for that presentation if you have registration to the conference. Please go to that presentation and consider that one as well. There we discuss also benefits of fractional control and where they stem from and so forth. But for now, thank you very much, and hope to see you again at different venues, and good luck in your professional career. And that's it from my side. Thank you.